Hello, everybody. Here's a quick little lesson on how a Taylor polynomial works. Where does this equation come from? How do things match? Um, if you look at the screen I have here, this is what a Taylor polynomial's general form looks like. So you'll have a number here, and you'll have a number times an x, and then a polynomial will increase exponents. So you could have a quadratic, which would go up to x squared. I'm going to only do this up through a quartic, x to the fourth, but I absolutely could go farther if I wanted to. If I'm going to use this function here, I'm just picking this random function. I could have used e to the x, sine x, whatever. But if I want to pick the function of ln of x plus 1, and I'm going to have it be a Maclaurin series, so it's going to have to match at 0, the function with the polynomial, and then hug each other around 0. What we're going to need to do here is, if we're going to create this polynomial, we're going to have to make the y-intercept, the x equals 0 spot, we're going to have to make them equal. So that's our mission. And not only that, that'll just make them touch at the y-intercept. We also have to make the first, second, third, and fourth derivatives also be the same. Then we'll have a pretty good approximation of the function of this complicated function with a simpler function, which is often thought of as a polynomial. Now, if they meet at 0, you're going to have the same y-intercept, but if your derivatives are all the same, then the increasing, decreasing behaviors will be the same, the concavity will be the same, the jerk behavior will be the same, so everything will be the same. So how does this work? Well, on the top left here, we have our polynomial general case, and for our purposes, that's the equation. So we're going to start by making them match when x is 0. So when x is 0 in ln of x, you're going to get ln of 0 plus 1, which is the ln of 1, and ln of 1 is 0. So I know that the x value is 0, and the y output needs to also be 0. So they have to match at 0, 0. So if I'm using my input as 0 in the polynomial, I'll also have to use my input at 0. And to get started, it's kind of easy. So if this is a 0, it'll cancel all of these terms, no matter how far I go. So the only thing you're left with is whatever a sub 0 is. And in this case, I need it to be 0. So in this case, my a sub 0, therefore, will be 0. So that step there is just getting the y-intercept so that these functions will match and touch at the y-intercept. So now, after that, we need to make sure our increasing and decreasing behavior is also correct. So increasing and decreasing behavior matches with f prime. So in my function, I'm going to make sure that f prime matches my derivative of p prime. So if f is ln of x plus 1, the derivative of ln of x plus 1 is 1 over 1 plus x, or x plus 1. But remember, since this is Maclaurin, we're matching it at 0, and we're hugging both functions around 0. So in this case, I'm going to make sure that when x is 0, the derivative also matches. So in my polynomial over here, I need to take the derivative of this. Well, if this was a constant, no matter what it was, we knew it was 0 from above, but no matter what it was, the derivative of a constant is, oops, sorry, I need to go back up here. This was our constant. So the derivative of a sub 0, even if it was 0 or 4, it doesn't matter, it's 0. But then how do I take the derivative of this second term? So the derivative of the second term is going to be the coefficient of x. So what's the derivative of like 4x? It's 4. What's the derivative of 10x? It's 10. So what's the derivative of a sub 1x? It's a sub 1. And if our function's result has to be 1 at the derivative of 0, then our polynomial's derivative at 0 also has to be 1. Therefore, a sub 1 is 1. So what I'm doing here is I'm trying to go step by step to try to figure out all these coefficients. So right now, that gives me the same increasing, decreasing behavior. And I could keep going with this, and I will, and I'll show you a little bit quicker here, but I want to show you a pattern. So if I take the second derivative, going back up to my original function, let me do some erasing here so you can see this. So in my original function here, if I want to take the second derivative, what happens here is the derivative of this is 0. The derivative of this is a sub 1. But if I take the second derivative, since that's a constant, that also goes away. These both go away. So how do I do the derivative of this? Well, the first derivative is bring the 2 in front, so it's 2, whatever a sub 2 is, times x. And if I take the derivative of that, then the derivative of that is just what's in front. So it's 2a sub 2. So if I go down here, that's where this comes from. So here is your second derivative. Now remember, Maclaurins are nice because we're doing it at 0, so the derivative of this doesn't matter, and this doesn't matter, because since it's 0, it wipes these out. So now my second derivative of the polynomial is this, and I knew because my function was that original ln of x plus 1, that if I take the second derivative, which is the derivative of this, I get this, and if I plug in a 0 again, I'm going to get this negative 1. So I know that the result has to be negative 1. So, well, what is a sub 2 then? If the result has to be negative 1 here, my second derivative polynomial has to match the concavity value of negative 1. So then how do I get whatever a sub 2 is? Well, I divide by 2. And that gives me negative half. And I will continue. So a little bit quicker. This is the same thing copied from the last slide. I need to go to the third derivatives to match. So what's the third derivative of this? The third derivative of this becomes this. Don't forget your chain rule there. Bring the 2, then it would be like negative 2, so you'd bring it in front, so that's where that 2 comes from, and then there's 2 negatives, which make it a positive. But then Maclaurin means at 0, so if I plug in a 0 to all of this, I get 2. Then this was my second derivative, so let's take the derivative of that. This is a constant, wipes it out. The derivative of this is the coefficient, so 6a sub 3. And yes, I could take the derivative of this, but if you notice, when you're plugging in 0, it wipes that term out. So now I get this guy. So then if I know this result is 2, I have to divide by the 6. Now, of course, you can reduce that to 1/3, but I'm going to leave it as 2/6 for now to show you a little pattern. And here is the same thing with the fourth derivative. So the fourth derivative, same thing. Once you get this result, you plug it in here and you divide to get that answer, and you get negative 6/24. So a couple things to notice here. Notice how I took the derivatives and the exponents keep coming down. So if those exponents keep traveling down, as you do this, you're going to keep bringing that like 2 in front. You're going to keep bringing that 1 that was there, and originally it had like that 6 there from the previous derivative. So interesting how that works. So then if you go over here, this is now my fourth degree meaning the highest exponent. It's my fourth degree of that polynomial, which matches this function. So now I can simplify. I don't have to write the 0, but I can. And then this is just 1x, and then this is just 1/2. But then this becomes 3. So notice how these bottom denominators here are 2, 3, 4. But I want you to notice that as you bring your denominators down, that 6 there, where does that come from? That comes from the original derivative of bringing kind of like that 3 in front. So this term right here. So when you take a derivative, it becomes 3a sub 3x squared. And then when you bring the 2 in front, it becomes a 3 and a 2. Now I could change it to 6, but if you see this pattern, even with the fourth, when you take a fourth derivative like that, the 4 comes in front, and then it drops to 3. The 3 comes in front. That's where these factorials will come from in your Taylor series formula. So when you're doing your Taylor series formula and you see those factorials on the bottom, for example, in the second degree term of a Taylor polynomial, you have x squared, because that's the second degree part, but the bottom is 2 factorial. Where did that come from? That come from taking the derivatives. And then, well, what goes here, that number is whatever your second derivative at the spot you're finding is. Likewise, for the third term, you have an x to the third. Well, what's in the bottom? Remember when you took your derivatives? You had a 3 and a 2. If you want to do the 1, you can, because it's easier to identify that as 3 factorial. And then what goes in front? That is the third term, so that's my third derivative, and a Maclaurin is evaluated at 0, but you can use any function and evaluate it at 2 if you want. Last thing I want you to notice is I want you to notice these two graphs. The blue graph here is your f of x, and the red graph here is your polynomial. And notice how they hug each other in this general zone here from -1 to 1. If you zoomed in on that, like right here, they are almost identical. Now, there is a little bit of gap here, so how could I clean up that gap? I could go to the power of 5, the power of 6, the power of 7. So that, ladies and gentlemen, is how you do a Taylor polynomial.